Hi, this is seventh video of the series of videos that I'm going to explain about quantum computing. In this video, I'm going to talk about syndrome measurement. So what is syndrome measurement? A syndrome measurement is to detect which eigenstate a given quantum state is. Syndrome measurement is the crucial tool when you want to make a quantum error correction. For example, ket0 and ket1 are plus one eigenstate and minus one eigenstate respectively of z-gate, and these two quantum states are plus one and minus one eigenstate of X. From now on, we're going to denote these two quantum states as plus ket and minus ket. So let's see the syndrome measurement Z. So here you're seeing a two quantum state, and there is a CZ gate, which is similar to C naught gate, except that it has Z gate instead of X gate, and at the last measurement is called the syndrome measurement. So here our concern is the bottom wire, which is called the theta qubit, and the top wire is called ancillary qubit. So this top wire only used to detect whether the theta qubit is stabilized in which state. So in this example, I'm going to initialize my ancillary qubit as ket0, and I'm assuming that my theta qubit is random, so I'm going to denote as alpha ket0 plus beta ket1. So what happens after I take a Hadamard gate? I get psi1 and I expand it to this summation, and let's carry on with the CZ gate. I get psi2 as follows, and then I apply the Hadamard gate on the ancillary qubit. So I get the psi3, the entangled state of 0, 0, and 1, 1. So what happens is when you take the syndrome measurement and record the observable as 0, that means your theta qubit is stabilized to plus one eigenstate of the Z gate. And when you take the measurement and record it 1, that means your theta qubit is now stabilized at ket1, which is minus one eigenstate of the Z gate. So syndrome measurement tells you which eigenstate the theta qubit is. It also stabilizes the eigenstate. What does that mean? So let's suppose I have ket1 on the theta qubit and the random quantum state for the ancillary qubit, and let's carry on the computation psi1 and expand it to the linear combination and up to psi3. What do we get here is reversed coefficient beta and alpha for the coefficient of ket0 and ket1, but still the theta qubit is stabilized at ket1. So we don't really change the minus one eigenstate of the theta qubit by applying the syndrome measurement. So far in this video, we talked about syndrome measurement briefly. In the next video, we're going to talk about how this syndrome measurement is used in the quantum error correction. Thank you.